Alright, so the problem is on Chapter 7 on kinetic energy, and it reads, the moon has a mass of 7.36 times 10 to the 22nd kilograms and moves about the Earth in a circular orbit of radius 3.8 times 10 to the 8th meters with a period of 27.3 days. Find the moon's kinetic energy as observed on Earth. Alright, so the unit sets given here is mass, which is 7.36 times 10 to the 22nd kilograms. The radius of orbit, which is 3.8 times 10 to the 8th meters. And time, the time to complete a revolution, which is 27.3 days. So from what we know of the kinetic energy formula, E sub k equals mass times velocity squared over 2, mv squared over 2. We already know mass, that's already given. What we need to know is velocity, and if you break down velocity, you'll get distance over time. And to find distance is a little tricky, requires some trigonometry. From what we know of its orbit, it's circular, so we just need to find the circumference of that, and circumference equals pi radius, 2 pi radius. So we just need to plug in radius, which is pi times 2 times 3.8 times 10 to the 8th meters, which will get you 2.38 times 10 to the 9th meters. And to find time, well, we already have time, it's just in the wrong units. We want seconds, not days. So you take 27.3 days, multiply that by the amount of seconds in a day, which is 86,400 seconds in a day, and you will get 2,358,720 seconds. So we have all the components for velocity. We just take the distance over time, which will equal 1,009.02 meters per second. Alright, so we have all components for kinetic energy now. So we'll just apply that to the formula. So E sub k equals mass, 7.36 times 10 to the 22nd kilograms, times the square root of velocity, which is 1,009.02 meters per second. All that is squared over 2. And the grand total is 3.7 times 10 to the 28th joules.
And the second part of the question is, would the moon's kinetic energy be the same from the sun's reference frame? And well, the answer is no, and the reasons why is kinetic energy is dependent on reference frame. So from the sun, the moon would appear to be going at a different velocity because it's a different distance, and also is dependent on the Earth's orbit. So that adds a completely extra variable that makes everything confusing. And also, another example would be like if you were on the moon yourself and you were standing still, it would appear that the moon's velocity would be 0, and therefore 0 kinetic energy. And strangely enough, if you started moving in one direction, from your reference frame, it would look like the moon is going under you, behind you, therefore giving you the kinetic energy. So it's all dependent on perspective. Okay, great job.